Hi, in this video we are going to see how to solve the problem in this example using a Verilog description. We have already seen in a previous video how to solve it using combinational blocks, and now we are going to see how it can be implemented in Verilog. Also, the idea is to realize that there are some parallelism between designing combinational circuits using blocks and designing it in Verilog. So first, before coding in Verilog, we need to have an overall idea of the solution. Okay. Now our problem is like this. We have a circuit that takes a data input of 7 bits. It's a character encoded with 7 bits, and we want to generate a copy of that code with 8 bits, where we simply add an additional parity bit. With that parity bit, the parity of the output data should be even parity in all cases. This is the first part of the example. Okay, so the basic idea is that we want to take this input t in, and we want to calculate the parity. So we'll have a block or some circuit or some Verilog code that will generate a parity bit for that input, for those 7 bits, and this parity bit will be added to this signal. Okay, so at the output we'll have these 7 bits combined with the parity bit to form an 8-bit of P data. Okay, it's important to note that these are 7 bits. This is just 1 bit that is combined with those. Okay, so here what we do is actually take 1, 2, 3, 4, 5, 6, 7 bits in TT in, and we combine with the bit coming from P, from the output of the parity generator. Okay, and we form the P data signal that now is 8 bits. Okay, that's what this dot here mean. We combine, we put all the signals together. So we need a circuit that just generates the good parity bit, so that when combined with P data is even parity. So this P should be, so P is equal to 0 when the parity of TT in is already even. Okay, should be 1 when the parity of TT in is odd, so that when the parity is odd, we generate a 1 combined with lines with odd parity will give a set of lines with even parity. Okay, I have said in a previous video we saw how to solve it, how to design that circuit using blocks, basically doing we have to implement a parity generator. That's all. In the second part of the exercise, in part B, we need to add let's call this part instead. Okay, not to be confused with the other one. We have to add an input signal P. So with that input signal, we control if we want the final parity of the data to be even or odd. So when P is equal to 0, we'll generate the output like before with even parity. When it's equal to 1, we'll generate an output with odd parity. Okay, that is for part B of the exercise. So I will put it in a different color. let's try again. Oh, it's more difficult than I. Okay, so let's put it in yellow color. Great. Okay, so let's start with the Verilog code then. Once we have a clear idea of what we want to do. So to do my Verilog encoding, let's create a small project. Let's go to our Verilog folder, new folder. Let's call it Parity. Simple that. Okay. And now let's create the files. Okay. We'll change the I will change the name and call it pargen, okay, from Parity generator. Okay, now we can create the files with our favorite editor. I will open it with, I will open the folder with VS Codium, okay, a text editor, which is a version of the Visual Studio Code open source project. And here I have opened the folder with the text editor. So now we can create files here. New file. Okay. And my file will be pargen.v. I start coordinating Verilog. So it's Parity. I'll call it adjust data parity. Okay. Module, putting some information so is always a good idea. And the date 30 November 2020. Okay, if there's some copyright information you may add, but for a simple example like this is not really necessary. And I will call it pargen. Okay. So looking at our problem, we have an input signal which is TT in and the output signal P data. I will just implement the first part. Okay. We'll leave the P for a modification. So we have input wire, we have 7 bits, 6 down to 0, TT in, and another the output. I think we'll use I don't really know what's going to be the implementation, but I think I will use a functional description. So I will use a wire 7 down to 0. This is P data. Okay. Okay, great. Our module ends here. And then we are going just to describe this thing. Okay, I will generate the signal par. That is the parity of the input data, and just output a P data, which is combination of the two. Okay, for the parity generator can be done just simply with an exclusive OR gate. Okay, the basically par this signal par can be built, okay, as the exclusive OR of all the bits in TT in. okay? Because this is the property of the exclusive OR operation. Basically, the circuit could be done just using a single exclusive OR, where we put here all the bits of TT in 0 up to TT in 6, okay? Basically, the exclusive OR is does this kind of function, okay? This will be 0 when parity is even and 1 when parity is odd, okay? Because anytime you change a bit, one of the bits here, the output will change from 0 to 1, okay? We've seen that in detail in the previous video. So we are going to generate that intermediate signal part. Let's define the signal. It's going to be a wire par, and now let's assign that function, okay? Because we already know the function. Assign par equal to the exclusive OR of all the bits of TT in. It can be done with the exclusive OR unary operator, okay? This is the exclusive OR operator. When we apply it to a multi-bit signal, it just does the exclusive OR of everything in TT in. If it's the first time we use it, we don't remember it very well, we can put a comment here, okay? Just doing the exclusive OR of all the bits in TT in. Okay, now that we have generated this signal here, I will just assign P data with this bit followed by the rest of the bits. It can also be done with a simple assign. Assign P data, and here we use the chain operator. Okay, we make create a new signal by chaining together all the signals. So we put par here followed by the original TT in together. That's it. And module. Okay. Let's check if it's correct or not. Let's open a terminal here and let's simulate it with Icarus Verilog. It's purging. Oh, it says no top level module. It's a very strange error here. Yeah, I missed the name here. It's assigned. It did not detect that mistake. I don't know why. Okay, let's try again. Input wire, output wire. Oh, I think that the semicolon doesn't belong here because it's a list of signals. Okay, it's not the. Let's try again. Okay, now my Verilog is not very fresh, so I still commit some mistakes. Okay, the description is syntactically correct. Now we want to check that circuit, so we have to write the test bench. Let's create a new file and let's do our test bench for gcb.v. A parity adjustment test bench. So as in any other test bench, we'll start with the time scale, 1 nanosecond, 1 picosecond. Okay, module test. And to do our test bench, we simply are going to do something like this. This is my hold circuit. So my test bench, I will do a very simple test bench. This is my module par gene. Okay, so I will basically implement a counter. I will define a variable that we will be incrementing, and I will connect that to tt_in, okay, through a signal here that is I will call tt_in as well. And basically that's it. Then I will check what's the result of my circuit. I will resort my 8-bit signal, p data, and to register the value we could generate waveforms, but we can use simply a monitor to make the Verilog simulator to print every change in the signals, okay, every change in my counter and the signal. I will print that signal in binary format and this signal as well, okay, so that we can check what's the parity of the data, okay, visually. So I will need a tt_in intermediate signal, and here I will use a p data intermediate signal as well. So we have two signals, wire 6 down to 0, tt_in, wire 7 down to 0, p data. We put an instance of my module or gene. This is my unit under test, and tt_in will be connected to the signal with the same name, and p data will be connected to the signal with the same name. Okay. Now the main part of my test bench. I need a counter. Okay, as I said. So actually, tt_in, which is my input, will be of type rec, because if I want to make a counter, it's much easier with an always. So I'll make my counter here, always, and every 10 nanoseconds, for example, I will increment tt_in +1. Okay, that's it. That will make tt_in to increment constantly to reach all the values. And now I need to initialize everything. I do it in an initial process. I will do many things here. I use begin here. And now I'll start by initializing my variables. tt_in will be equal to 0 at the beginning. And that's it. Now this process here will be incrementing tt_in. We just need to program the simulation, to configure the simulation, okay? So we'll make a start by, if we want to generate waveforms, okay, we can do it with dump file, par gene tb vcd, and a dump vars directive 0, test. Okay, this will generate all the signals in my description. Okay, if we don't want to use it right now, we can leave them commented out just for later use, because as I said, we don't really need that. We can simply display the results in the terminal. So this will be a header that says this is tt_in, okay, and we'll print here p data, and let's put some space here, okay, and then simply we'll monitor all the changes. Okay, our monitor will print a binary number, which is the tt_in in binary format, leave some room, print another binary number, and this is our format string. Okay, the numbers will be taken from tt_in and p_data. So the string describes the format, and this is what it will be substituted here, and this value will be substituted here anytime something changes. Okay, so that should be enough. Only we need to finish our simulation at some point. Okay, tt_in is 7 bits. It will take 128 different values. Okay, so we'll may stop. We don't have to go through all the values if we don't want to do it, but if we want to do all the possible combinations, we'll have to run our simulation for 125 times 10 nanoseconds. Okay, so our finish will be at least at this time here, approximately. Okay, it will print a lot of lines, but let's do it like that. Finish. Great. We'll end and module. Okay, in the Verilog course, you may find other test bench that, for example, in many examples, that generate a random number, that test a circuit by generating random numbers. So sometimes, if you don't really want to test all the possible inputs, you can just generate, use that test bench and generate a few numbers only. Okay, let's save it. Let's now compile with the test bench. It's, oh, we have no problems here. So let's execute the simulation. VVP a.out. It will generate, okay, lots of signals here. If we scroll up, we should have here all the possible values in binary: 0, 1, 2, 3, 4, 5. Okay, these are all the possible input combinations. Now the result is the same number, but preceded by the parity bit. Okay, we can check not all, but a few of them. For example, in this case, we have the same number. This is number 14, I think, but it has one here to make the parity even. Here, the parity bit is 0 and makes the parity even. And you can check that every time the parity of the original number is odd, the parity bit of 1 is added to make it even. Okay, so it's really nice to see. Okay, don't you think so? It's working perfectly. Okay, what if we want to do section 2 of the exercise? It means add a control signal here to adjust the parity. We can do that. Basically, it means that in our design, now we want that this circuit will generate, this parity will be 0 for when p is 0 or 1, or so will be be a 0 when the parity is even, but if this is 1, it will be a 0 when parity is odd. So we want to transform even parity in odd parity. Okay, so basically when this signal is equal to 1, we have to, this value we generate will be the opposite. It can be done in different ways. Okay, and so let's go back to our design and we'll make that change. We have an additional input, wire P. Okay, it's good practice to put some comments here. Input value, output parity that we want to get. Okay, a 0 here, it means we want even parity. 1 here means we want odd parity. Output value with adjusted parity. Okay, great. So now the solution is very simple indeed, because we can do it actually here, okay, in different ways. For example, we can do it in different ways. In this case, we want to take a decision depending on P, okay? If we don't want to calculate the function, actually, we can modify it a little bit. So instead of using a continuous assignment for par, we can change this one. We can change this wire and convert it in a rec, so we can operate it into a process, okay? And we convert that into a combinational process. We do an always. So here, this is combinational at asterisk. So now part can be assigned, and we can take decisions here. So basically what we do here is that to describe the procedure, if P is equal to 0, okay, we do what we did before, okay? We assign par with the exclusive OR of all the bits, okay? And if we in the other case, okay, it means when P is equal to 1, okay, we assign par with the opposite value. So we can say simply par is the opposite to the exclusive OR of all the bits in TT in, okay? This is an option that we can change. So you can see that we simply change to a procedural description because the behavior is a little bit more complex now. We feel more comfortable to taking decisions, so we can change at any time. So anything, we don't have to change anything else. This process will be assigning par with the right value, and at the same time, this continuous assignment will be assigning P data with the right value, considering the par here. We save that. Let's check only the design to see if we have syntax errors. We have some of them. And Verilog didn't like it because I forgot to put the assignment operator. Okay, let's try it again. Okay, now let's compile with everything. Let's simulate. Okay, but now, yes, I will have to change our test bench. In order to try our test bench, what we are going to do, not complicate it much more, we are going to use a par here, okay? So we are going to we have to include P input, and we are going to assign a constant value, okay? We can assign a constant value like this, P equal to 0. Okay, let's try this. I think this is correct. And then we'll include it here. We assign the TT in, and now we also assign the P signal. Okay. So basically what we have done in our test bench is that now our part generator have a P input. So we have included the Verilog code to assign a value here. What we are doing here is to put some Verilog code that simply assigns a constant value, okay? Makes p equal to 0. That's what this definition here mean, okay? We declare the variable at the same time we assign value 0. This is equivalent to declaring the variable and doing a continuous assignment, okay? And assign p equal to 0 below here. Okay, so we can test with p equal to 0 if we want to check p equal to 1. We can copy the comments because this is easy to forget. So we can put a comment here, and actually we could put a comment here and here as well. Okay, so let's save everything. Let's compile with the test bench vvpa.out. And now we should get the same result that we had before. Because we have selected p equal to 0, the parity should be always even. We see it's even here. It was odd, now it's even. It was even, now it's even. Okay. Now let's change it to 1. If we let's compile again, simulate again. Okay, now the resulting parity should always be odd. Let's check here, for example, this is 5 ones, it's odd. Okay, it was odd and it is odd now. Okay, before here it was even, it is odd now. And we can check all the cases if we want. Okay, 5 bits, 5 bits. Let's go to the initial cases. Okay, it's even odd, 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 even odd, odd, even odd. Okay, so that's great. Our circuit works right when we select even parity or odd parity. Okay, so finally, this is basically our example on how to describe in Verilog a problem like this. Okay, and what's important to note here is that the way to think when we are using blocks, it's also useful to write language, hardware description language. We think of what my circuit have to do more or less, and now these blocks, this functionality, we know we have to implement instead of combining or the well-known combinational subsystems. We just make a Verilog description for them. Okay, so that's it. Thank you.